The last class.
Sir, we did those problems.
Yeah.
Problems, no, sir. We did.
Problems.
Yes, sir. Those till that.
Only problems.
No, sir. I'm telling till that problems will
Uh-huh.
finish, sir.
Yeah. 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 Any like you want to summarize what we have discussed, right? Or anyone?
Sir, we mainly covered topics like slip systems and the planes, the angles with respect to slipping of a crystal also. So,
Yeah. 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 Anyone? Any other student? What Amal missed? No one. I think we are not studying at home, right? Maybe only few students just responding in the class, also reading. And we will make the quiz in Friday. Is it okay?
Fine, sir.
Yeah, in the last module, Friday is okay or Tuesday? Because anyway, we will just study in the before night. Yeah.
Yes, sir.
So module is already working.
Sir.
yes, sir.
Module. Yeah, because yesterday or day before yesterday we have received email.
Yes, sir.
So I
Yes.
think we have now new user ID and password. Yeah.
Yes, sir. Yes.
Yeah. Okay. So if it is working for all, then we can go for Friday. Okay. Maybe 10 MCQs. And the last module, not this module. This module you don't need to study. Only last module, whatever I have uploaded in the MS Team, that only you can download and you can study. Okay, 10 MCQs, and maybe I will give 10 minutes or 15. 10 minutes will be okay, I think. Yeah.
Okay, sir.
Or you want more?
Sir,
13,
15 minutes. Yes, sir.
Okay. 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 So I will make 15 minutes. Okay. Yeah.
Sir, what, sir? I just joined now, sir. What did you say, sir?
Who?
Sir, I just joined. What did you say, sir?
I told we will make the quiz of the last module, whatever we have studied. We will make on 4th February. Okay, in the class time. Maybe I will teach first half an hour or maybe 40 minutes, 35 minutes. Then we can go for the quiz in the last. Okay.
Okay, sir.
Okay. So if all the material is already uploaded in MS Team, you can download and you can study. You know, I think Satya, you were in my last class. So you are aware of what we are making. Yeah.
No, sir. For today, I joined late, sir. That's why
Okay,
I'm
okay,
asking.
okay, okay, fine, fine. Okay. Okay, so in the last class, just only I want to summarize what maybe I will add something what Amol missed. So initially we have talked about the different kind of plastic deformation. What we had, one is sleep, then twinning. The most important what we are talking about sleep already we have covered in the last class, and today we will cover the twinning part. And then apart from the sleep and twinning, also we have the plastic deformation modes or the mechanism. One is phase transformation, then another one is the creep mechanism, then also the grain rotation or maybe the what we are telling. Apart from this, also other mechanism we have, but we are not going detail phase transformation, creep mechanism, because these are related to other subject. But of course, we can at least we should know that what are the modes or the types of plastic deformation are there. But we will cover here sleep and twinning. Okay. Then we talked about the plastic deformation by sleep. I have given one example of that, the movement of the caterpillar. Okay, how the shear stress if you have initially, then how you are when it is the plastic deformation is going or happening, then how it is moved or how it is shifting from one to another place. Okay, so with the help of that Berger vector, that one also we have discussed. Then we talked about a little bit of that, edge dislocation and screw dislocation. Maybe details I have not gone because you have already studied, because we cannot go again, the initial basics. So, what I told, the edge dislocation lines, these are normally moves parallel to the whatever the stress you are applying. Whereas if you have the screw dislocation, these lines are moves perpendicular to the stress what you are applying. And the next we talked about the sleep system, what Amal you were pointing that sleep system, it actually consists of two things. One is the sleep plane and the sleep direction. So that means in which or specific direction actually it is going, or maybe the dislocation is moving. That also we have talked. Then we talked about that block diagram I have given you. So if this is from microscopic, then how we are going to macroscopic. Okay, so that means how the dislocation actually it is going from the macroscopic to macroscopic level or macroscopic change. Okay, so I put two block diagram, it was the rectangle or maybe the square one, and then how you make it rhombus, how it is going step by step. Okay, so then finally we got the net shape. Okay. Then next we talked about the P and stress, the Pons and Nabarro equation, where we are thinking about the critical stress there. Okay, and this equation was tau Pn equal to G e to the power minus 2 pi n by B. Okay, where B equal to the Berger vector and W equal to the width of the dislocation and G equal to the shear modulus. Okay, so these are also we talked. And then later we have talked about the single crystal. If you have, I have given one zinc single crystal, and then how actually it is moving when you are giving the tension, in the both this side. Okay, how the slip plane actually it is changing, or you can see in a different version. Then finally, we have talked about the critical resolve shear stress. So we have defined initially what is RSS and what is the basic meaning of the CRSS. And based on that angle, like, this stress to make the angle of the slip plane and the slip direction, the theta and phi. And based on that, we have done a few numericals. Okay. So we have done up to the slip mechanism. So today we will cover about the plastic deformation by twinning. Okay. So I have given here the schematic diagram in the bottom. You can see here in the left hand side. So the first diagram was based on slip, because just I want to put here so that you can differentiate how actually it is, from if you will see by the naked eye. So how we can differentiate. Of course, I have one slide, the textual, like, the slip and twinning. I made a differentiation. So maybe again you can cross check. If you want to add some points there also, you can add. So in addition to slip, dislocation movement, plastic deformation can also occur by twinning. So what I said in the beginning, in the last class, so I put one schematic diagram here. So apart from this slip also there is a twinning. So based on that twinning also, we can make the plastic deformation. And twinning is a shear force that can produce atomic displacement. Okay, so again, if you have, of course, this material is contents of the atoms. So if you are displacing the atoms, so normally this is basically called as a twinning. And the twinning results when a portion of the crystal takes up. You can read the definition. Crystal takes up an orientation that is related to the orientation of the rest of the untwinned lattice in a definite symmetrical way. Okay, so normally we are calling this is as a, like, the mirror effect. For example, if you will see here in the right hand side, the schematic diagram. So you can see here three things I mentioned here. The circle one, atoms that did not move. Okay, you can see here. Maybe it is very small, I think. Probably if you will see very clearly or maybe very deeply, you will find the circle one. Okay, the upper part, the circle one, these atoms that did not move. So that means this is not moving after the the twinning. And the dotted one you can see here. The dotted one is original position of the atom. Okay, so these are the original position. Okay, and the black particles or the black atoms, these are the final position of the atom. Okay, so that means whenever you have the right hand side photos, you can see the dotted one. From that dotted one, it is moving to the dark atoms. Okay, but other the circular one, it is not changing. So you will find this is a mirror image of this side to that side. Whenever it is changing, so both this side it will same. You can see here. And if you will see this clip here, so that means the layer actually. So there it is changing. But whereas in twinning, this is the whole area it is changing in one path. Okay, so it is not changing by in the separate plane. Okay, so this is the basic meaning of the slip and twinning. And the twin portion of the crystal is a mirror image of the parent crystal, and the plane of symmetry between the two portions is called the twinning plane. Okay, so if you'll see here, So this is the twinning direction in which way actually it is moving, and this is known as the twinning, and this is known as the twinning plane. Okay, and the twinning may favorably reorient the slip system to promote the dislocation moment. So if you want to reorient it, whatever I told you, the original position you had, then again it is moving that. So if you will make in this way, so both the side you will find this is a like mirror effect, and both the side it will be same. You cannot tell that it will be different. For example, you can see on the top portion and the bottom portion, it will almost same. Okay, is it clear? Yeah.
Yes, sir.
Yes, sir. Yes, sir.
So now the when we are thinking about twins, now also we have to differentiate, because if we go very deeply, normally we are talking every time like overly, because these things also we know, because sometimes like I gave one example of that the towel, for example, after taking shower, then how we are removing the water. Okay, so we are squeezing that one. Maybe that example I have given somewhere. So here also twin, you cannot tell that this is only one kind of twin. So twins are generally of two types. One is mechanical twins and second one is annealing twins. Okay, maybe some students, why we are going little deep, because now just theoretical we have studied. Maybe some students, they are much more interested about maybe metal forming. So we are also relating to that research side, because we are not doing only academic side. Some research part, of course, theoretically we are doing. So maybe if you are interested, maybe you can go ahead in future. So one is mechanical twins and second one is annealing twins. Mechanical twins are generally seen in BCC and HCP metals and produced under conditions of a rapid rate of loading and decreased temperature. So if you remember when we talked about how to remove the internal stress, so we talked about the heating rate and then also the holding time, then also the cooling temperature or the cooling rate, right? So here also the load also I have told you sometimes the load also this depending upon the load actually how much you are giving, and this load also whether you are giving slowly or whether you are giving rapidly, that also it will create some impact there. Then second thing, of course, we have studied about the effect of the temperature. Okay, so whenever you are increasing temperature, also something will happen, and when you are decreasing the temperature, also something will happen, and that also depends upon rate. Okay, so rate of decreasing or rate of increasing. Then second one, we have the annealing twins. So the annealing twins are produced as the result of annealing. Okay, so whenever you are making annealing, that means heat treatment, also you are finding they are annealing twins. And these twins are generally seen in FCC metals. Okay, so these are the some people they have already done, so established. But if you want to check, you can take some BCC crystals or maybe some HCP metals or maybe some FCC metal also you can take, so that you can check, because it will not take a long time. Maybe you can think about the temperature, how much temperature you want to increase, in which rate. But the moment you will take it very slowly, it will take maybe a lot of time. Let's say if you have a metal, you are taking 600 or 700 degrees C, and you are increasing only 1 degree C or 2 degrees C per minute, it will take a lot of time. Okay, but of course the heat treatment process is like this. But how we will observe that whether this phase transformation or the phases from X position to Y, or maybe this time X duration to Y duration, how it is changing. So you have to stop the experiment somewhere. Then again you have to check, you have to take it out. Then again you have to go for any the morphology test. For example, any scanning electron or maybe the electron microscope, so that you can see the morphology. And the annealing twins are usually broader and with straighter sides than the mechanical twins. Okay, so if you will see the schematic diagram here, I have given here the mechanical twins, the Newman band in iron. Okay, so the first one, the A part, first picture. And the second picture is mechanical twins in zinc produced by polishing. Sometimes when you have, I do not know whether you have done our material characterization lab, we have some polishing machine. So sometimes maybe I do not know whether, because I didn't check actually. So if you will go to any research laboratory, so sometimes, I have this experience also, because sometimes we are, without polishing, we are going for the microstructure testing. So in that case, you will find many, the layer, some impurities or maybe something on the top surface. So it will be very difficult to find out what are the, elemental or the microstructure or maybe the phases are there. It is very difficult because you cannot distinguish, because a lot of impurity will be there. But if you want to polish it, so that means inside you do not have any impurities or maybe less impurity. So you have to polish it. But the moment the polishing machine is rotating, but you can or you are putting the sample by your own hand, then our hand is not stable, so it is vibrating. So in that case, what will happen if you will take that sample and you will put in microscope? So you will find a very rough surface. But what for a research purpose, what we are doing, we are putting a stand there. And with the stand, we can fix the sample there. So it is like, fixed. So that means the stand is not moving. Only your the police machine or the the paper you have, the emery paper you had. So that one is moving. So your sample, you will find a very clean surface or very flat surface. So in that case, it will be very easy to find the microstructure. And whenever you are putting in a scanning electron microscope also, it is good, because normally the beams actually you have to put in a parallel surface. You cannot put a zigzag surface. Okay, so you'll find this kind of microstructure. You can see this is not so clear, but still you can find this kind of different structure. And the third one, you have the annealing twins. In annealing twins, this is gold and silver alloy. Okay, so you can see the grain boundary, how it looks like. Okay, maybe I will show another photo somewhere after deformation also how it is happening. Okay, is it clear? Yeah.
Yes, sir. Yes, sir.
Okay. Yeah. So then we had I put some some database of what we have, the twin planes and the twin direction actually. So if you have the crystals, so I will go in the beginning. So the twinning generally, of course, when the slip system are restricted or when something increases the critical resolve shear stress. Okay, what we had discussed in the last class about the CRSS. So when the CRSS you are increasing, or when the slip system you are restricting something somewhere. Okay, so then your twin actually it will happen. So the twinning generally occurs at low temperature or at high strain rate in BCC or FCC metals or in SCF metals. Okay, so you can see, you can just cross check if you have three different kind of or variety of samples you have, then you can go for the whether how the the deformation or how the stretching of the grain boundary or how the stretching of the grains actually is happening. So just you can cross check. And these are the basic crystal structure we have, and the typical example also we have taken. Maybe based on this, you can just take one sample for each, for example, one BCC and one HCP and one FCC. Then you can see that or how the planes. But if you want to go for TEM, of course, we do not have here. So if you want to go for TEM, maybe it will be much more clear about the in nano. If this is very small grain structure and you cannot see by scanning electron microscope, you can go for the TEM. But you can find in SEM also, you can find. There is not an issue. Okay. Yeah. So this slide is much more important now. So I have given very few points here when we want to compare, because if you know the slip, maybe somebody will ask you what is the basic difference between the slipping and the twinning. So in that case, you have to distinguish by yourself. Okay, so I have given again one schematic diagram which difference between the slip planes and the twin planes. Okay, what I have shown in the previous maybe 2-3 slides back. So these are the slip planes actually you had. Then again it is moving. You are giving the stress here, but at the opposite stress also you had here. But similarly here also in twinning, your the total surface, the total one it is moving. Okay, so not like different slip planes. The total, the average one or the big size, it is moving in one side. So I mentioned how to differentiate the in case of slip, the crystallographic orientation above and below the slip plane is the same both before and after the deformation. Whereas in case of twin, the orientation difference is seen across the twin plane. Okay, so this is the basic difference. In then second, the slip occurs in distinct atomic spacing multiples, and whereas in twins, the atomic displacement for twinning is less than the interatomic separation. Okay, so these are when you will study little deep, and then maybe or when you will do some kind of research now only theoretically. So maybe it is very difficult to predict that how actually it is happening. But maybe the first line, I think you can be much more clear. And the third one, we have the slip leaves a series of steps lines. Okay, so these are also from first line also you can make it clear. And in case of twinning, the twinning leaves a small but well-defined region of the crystal deform. Okay, so whatever the region we have or whatever the space you are deforming or you are twinning, so that one clearly well-defined because the big area. So it is very clearly defined that this area is twinning. And here in case of slip, normally slip results in a relatively large deformation, where in case of twin, only small deformation results for twinning. And slip, normally the example what I told in the previous slide, most seen in FCC and BC structure, whereas in twin, and this is normally happens in HCB structure. Okay, so these are the basic difference. But when you are studying the book, maybe if you can find some other points also, you can add in this slide and you can share with me. Okay. Okay, fine.
Yes, sir.
Okay. Yeah. So next one we have, we talked about the single crystal in the last class when we talked about the zinc metal. In both the case when we are making the tension or giving the force there, how actually it is happening. That squeeze kind of structure I have shown you in the last class. But now in talking about single crystal, but now we are going for polycrystalline materials, how actually it is happening. Okay. So the plastic deformation in polycrystalline materials is very complex than those in the single crystal due to the presence of grain boundary, different orientation of neighboring crystals, presence of several phases. Of course, if you take one more example, sometimes when we are studying the BTech or maybe MTech, so lots of you have the credit. For example, you have the open credit, you have the core credit, you have the elective credit, and you have the non-credit. Lot of things. But when initially, for example, if you remember when you were in first semester, a lot of questions to the proctor. Okay, so this one is not happening. That one I do not know what is this, what is that, and you do not have this patience also to study all the the rules and regulations, whatever the university, any university, they are providing. So in that case, it will be much more complex. But the moment you are moving to second semester and third semester, then if we have some doubt, we will ask you because you are much thoroughly in that particular aspect. Okay. So similarly, if you have a single crystal, so that means you do not worry about other things, other parameter. But whereas if you have a polycrystalline material, so that means it is a mixed one. So it will be complex, of course. So why this is complex? Because the presence of the grain boundary. You can see the schematic diagram. If you will see, the lot of the grain boundary, for example, you can see these are the grains and these are the slip planes, for example. So it will be much more difficult to understand how actually it is happening. And second is different orientation of the neighboring crystal. So if you have one crystal, then another crystal is there. So also you will find very different. Okay, you will not find very similar way. If you have single crystal, everything is same. So for you, it will be easy. And third one, we have the presence of several phases. Okay, in polycrystalline material, several phases are there. So it will be much more complex to understand how this plastic deformation is happening. Due to the random crystallographic orientation, the slip planes and the slip direction varies from one grain to another. Okay, so if your crystal orientation or the crystallographic orientation is different or is not in a order, it will be in a disorder. So it is very difficult to find out the slip lengths and slip direction, and also of course it will be different from one grain to another. As a result, the resolve-shear stress will vary from one crystal to another. So if something is different from the beginning, so everything will be different. So when we are looking, for example, when you are adding to a water, let's say you are adding sugar. So one thing you will find, because only you have added sugar, but the moment with that sugar you are adding salt or you are adding any other chemicals or maybe compound, then it will be very difficult to find out something. So when we are doing some research, we are avoiding a lot of complex things. We are just thinking if one part or two part is there, then probably it will be easy for me. But of course, you cannot avoid sometime because you have to add to generate something. Then in that case, you have to think about or you have to predict your mechanism or your if you have some chemical reaction, you have to propose your chemical reaction. You cannot tell that exactly this is same what you are predicting or expecting. So when a polished polycrystalline specimen of copper is plastically deformed, two slip systems operate for most of the grains, evidenced by two sets of parallel yet interesting sets of lines. So for example, if you can to take any polycrystalline copper specimen or or any other specimen, so two slip system you have to operate there. Okay, you cannot think that only one slip system is there. Okay, so if one more than one, then probably it will be much more complex. Of course, you can do it, but initially you will find a lot of stress there because lot of parameters you have to choose. For example, you told maybe in the beginning of the classes we know ANSYS. So ANSYS means you are thinking just only in a small parameter, maybe 5 or 6 or maybe 10 parameter. But when you are going to a company, so they will give different tasks. Now, in our small mind, we are thinking, the X parameters. But we have to think there because they will think that you are working or I'm working. So they will give a little complex parameters or complex job. So in that case, you have to think different parameters. Like, is it clear?
Yes,
Yeah.
sir.
Okay.
Yes, sir.
So then one more photos I just share with you, the scanning electron microscope. Also during deformation, the mechanical integrity and the coherency are maintained along the grain boundary. That is, the grain boundary usually do not come apart or open up. So whenever you are doing any kind of the mechanical testing or any kind of test, so your mechanical integrity and the coherency also you have to think about near to the grain boundary. As a consequence, each individual grain is constrained to some degree in the shape it may assume by its neighboring grain. So because you have to think about whatever the behavior of the neighboring grain, also it is behaving to the X grain. Okay, you cannot tell that that grain is different and this grain is different. So there is no interlink between that. No, there should be some interlink because this is connected there. So there should be some bonding, or there should be something happen, or maybe some chemical bonds are there. So I put two schematic diagram here, the alteration of the grain structure of a polycrystalline material as a result of plastic deformation. Okay, so whenever, if you will remember, in the beginning of the classes, I put some schematic diagram. Your deformation zone is there, then your lubrication is there, your both the way your force is there, then you have some energy evolve is there, then you have some friction is there. Okay, then also in one slide I have shown how the grains actually it is evolving. Initially you had some grains, then it is stretched, then again you will find some small grains, then again it is growing some the recovery recrystallization grain growth. Small grain it will generate there, then again it will grow, then finally it will go to the grain growth. So that after that you cannot make it larger or make it in a growth stage. Okay, so that means this is already established or in a growth area. So the first one, the first part, the A, so this is before deformation, the grains are equiaxed. Okay, so that means this is before deformation. So you can see the grain size and grain particles. Okay, so this is almost like, I'm not telling that all are equal, so but this is almost equiaxed. But whereas in B, if you will find in the second case, so after deformation, elongated grains are produced. So that means when you are deforming, whatever the grains you had already in the first graph, so this is now elongated. So that means this is now enlarged because this is stretching there. Okay, then after that, then you will find something like, in a different stage, because it will be already grain growth, but now it is stretched. So that means after deformation, you are finding this grain. So if you will see, like, because now I am showing the photo of one kind of structure, but when you will do by yourself, it will be much more interesting because you will see by your naked eye. Okay, so this is the basic, the twinning and how you are finding the crystal structure or the grains or maybe the morphology of this surface. Okay, is it fine?
Yes, sir.
Okay, so I think one more slide I have, the yielding criteria. So almost we have done many things, but maybe I need another one class probably. So now in yielding criteria, so I think we have discussed maybe in the last module probably. Just I put one or two hints there. So one is the problem of deducing the mathematical relation, because whenever we are doing, I asked you maybe sometime why you are going for the mathematical modeling or maybe the simulation, why you are going that one. Maybe somebody told, I don't remember. So maybe I will ask you one question. Whenever you are doing any kind of experiment, so you are going for ANSYS or maybe you are going for XYZ, any kind of simulation. So can somebody tell why you are going for that simulation or maybe the mathematical modeling? What is the basic motto of that, or what is the basic aim of that? Anyone?
Sir, in order to validate the results or understand the differences, the values obtained in between the experimental and the analytical way of solving it.
Any other? What Amal is telling, can somebody tell he's right or wrong? Anyone?
So validate, yes, to some extent, but you want to do it before you actually do it in real life, so you don't have to cut material and waste it.
Yeah, this is who, Avito, right? Okay, so any other you want to add to Amal and Avito? No one?
So
Because
one more,
yeah, add it.
in real life, when let's say for example we build a metal table or something, it will not show me where the stress is going to be high. It will directly fail over there after 1 year. But
Yeah.
with simulation, I can say show me the stress plot and I can see where it is actually weak and I can increase that thickness or whatever.
Yeah. Any other? Yeah, this is true, because whenever we are doing any kind of simulation we are doing before experiment, right? Is it correct?
Yes, sir.
Yeah, because why we are doing? Because if, for example, you can go 20 years back when people they were doing experiment. Maybe at that time simulation very rare, and if you want to buy that software also, it was a lot of expense. It was expensive, so you could not buy also. So what we were doing, for example, if we go to the phase diagram, let's say. Okay, the metal melting, what you have studied, maybe A and B, like, alloy, you have to find out a big diagram. So how they have plotted that diagram? They have done experiment in each stage, then they found out that point, then they plot the diagram. It was very complex, and you cannot do within, like, 2 months, 3 months, 6 months. They have to repeatedly, they have to do experiment. They have to waste lot of, the experiment samples, then they have to waste time, a lot of things, what Amal or Abhito they said. But if you have the simulation or the mathematical modeling, so you can predict something there. Maybe how much stress, what Abhito was telling, how much stress maybe we can apply. Maybe how much, heat maybe we can generate. We can predict something. I'm not telling that this is exactly what we are predicting. This is true. Maybe it can true. Maybe it may not also. But maybe we can at least predict something. Okay, like, the weather forecast, what we are doing. So we are just predicting. But, if you remember 10 years back, let's say when you were maybe 10 standard, or maybe, like, maybe 6, 7 standard. So at that time, our radar was not so, like, high powerful or caliber. So they were not predicting. Maybe if they will tell that maybe tomorrow it will come, but maybe it will come after 2 days, right? But nowadays you can see. So how they are predicting in a precise way, so that when they are telling, and which place also they are telling, almost like, maybe 95% close to that area they are making. Okay, so similarly, if you have any kind of simulation or any kind of mathematical modeling, so you can predict something, so that you can decrease your experiment numbers. Also, you can save your time. You can save your samples or maybe the consumables. Everything, it will be much more better. And also, when you are projecting somewhere, so you can tell that this is my the prediction, the database, and this is my experiment. So now this is matching. So what you are telling, that how to validate. Okay, because we are not doing experiment, then we are doing the simulation. We are doing simulation first, then we are going for the experiment. So that you have to validate, right? Is it clear? Okay. Yeah, so I mentioned that the problem of deducing the mathematical relationship or predicting the conditions at which the plastic yielding begins when a material is subjected to any possible combination of stresses is important. So what I mentioned here, so that means when actually the yielding begins, that also you can predict. Then what kind of stresses are required there, okay, or what kind of stresses is passing in that area, also you can predict there. Okay, in uniaxial loading, as in the tension test, macroscopic plastic flow begins at the yield stress sigma f. Okay, it is expected that yielding under a situation of combined stress can be related to some particular combination of principal stresses. Okay, so these are already we have discussed about the sigma h equal to sigma 1 plus sigma 2 plus sigma 3 by 3. Okay, the principal stresses divided by the 3. Okay, this one maybe we will discuss maybe in the next class also a little bit. Okay. And the yielding criteria is essentially empirical relationship. But that's why I asked the question, because the yielding criteria actually you cannot do by experiment, or maybe you cannot predict very exact thing. So these are basically depends upon the empirical relationship. Okay, so you are predicting something. However, a yield criteria must be consistent with the number of experimental observations. So why we are doing, and for example, if you remember your lab classes, so we are every time taking 3 readings. Why we are taking 3 readings? Because we are just checking whether whatever I have done in the first experiment, whether this is right or wrong. So we are making confirm again in the second reading. Again, we are going for third. Then we are making the average one for the third. And the hydrostatic component of a complex state of stress does not influence the stress at which the yielding occurs. Whatever the hydrostatic stress or hydrostatic pressure we have covered, the delta H equal to the delta 1 plus delta 2 plus delta 3 by 3. So that also you have to think about. And also, therefore, we look for the stress deviator to be involved in the yielding. Stress deviator means whatever the remain when you are when you are making minus the hydrostatic component, so that you are finding the stress deviator. Okay, that also we have covered in the previous classes. And moreover, for an isotropic material, the yield criteria must be independent of the choice of axis. That must be an invariant function. Okay, whenever we are thinking about the empirical relation, then we have to assume something. Otherwise, you cannot go for that. Okay, so there are two generally accepted criteria are there whenever you are making the prediction of the onset of yielding in ductile metals. So one is known as the von Mises or the distortion energy criteria. And the second one, we have the maximum shear stress or the Tresca criteria. Okay, so these two things, I think I have shared some of the hints actually somewhere. So I didn't explain everything because we should teach here. So maybe in the next class, we will talk about what are the basic, like, one slide, maybe I will share. Some not derivation. I think the equation I will share, because the derivation it will take time. So one is the von Mises or the distortion energy criteria, and second one is the maximum shear stress or the Tresca criteria. Okay, so these two we will cover in the next class. Okay. Yeah.
Yes, sir.
Any question from your side?